Good afternoon. I'm Davide Poli, and this is my presentation for the doctoral meetings of my fourth year of PhD on advanced 2D fluid modeling of all effect thruster discharges, supervised by Pablo Fajardo and Eduardo Edu. So the motivation of my thesis is the problem of the anomalous transport in Hall effect thrusters. The problem of anomalous transport, we believe it's due to the onset of plasma instabilities, and it's common to many cross-beam devices. And this is why in my thesis I studied other e-cross-beam devices than the Hall effect thrusters. So as a brief recap of my first years, I started simple by developing a one-dimensional quasi-neutral time-dependent model in which we included a lot of physics with respect to the literature, and that allowed us to study the discharge and its dynamical behavior in the breathing mode, in the axial direction, where we observed the breathing mode and the effect of neutral modeling on its onset. The main results are the onset of a breathing mode that is dependent on the physics that we select. For example, here we can see that with the simplest possible model, where we do not consider heavy species energy equations or azimuthal inertia, we can retrieve the breathing mode if we increase the anode magnetic field, while here we can see that as we add more physics, we don't get any more a breathing mode by simply increasing the anode magnetic field, which is in this direction for larger LM1 parameters, but we need to give also an energy input on neutrals, which means that the neutral dynamics affect the ionization instability, but it also shows how the breathing mode instability is sensible to the physics that we're modeling, to the phenomenological parameters that we are considering, and the main take is that it's extremely difficult for one-dimensional model to isolate the trigger mechanisms of these instability. And this is a little bit in contrast with the literature, where a one-dimensional model are used to look for this trigger mechanism. We also noted that there's a wide range of parameters for which the model fails because we reach the collapse of the anode sheath, the anode potential drop, which assumes subsonic electrons because it's an electron repelling sheath. But we've seen that during strong breathing mode, especially in conditions of strong magnetic field at the anode, the sheath goes towards a zero potential drop, and then the model fails. So we asked ourselves what is going to happen. These results have been published in 2023 in a journal paper for Journal of Physics D, Applied Physics. So we developed a one-dimensional non-neutral model, which is an extension of the previous model and allows to resolve the transition to reverse shift by assuming full electron inertia and the Poisson equation. We also had to input, to add appropriate boundary conditions that could allow this transition. So as you can see on the right, we can see reverse shifts. This is the forces in the momentum, axial electron momentum balance. We can see on top that in a normal sheath, we have that the pressure gradient balances the electric force, while in a reverse sheath, this is not the case. And the electric force is balanced almost uniquely by the electron inertia. So this is fundamental to resolve this kind of sheaths. And of course, the derivative diffusion approximation is no longer valid. So we started experimenting with the anode magnetic field and to trigger these anode sheath transitions. And we saw that the reverse sheath is unstable. So we cannot operate the thruster, have a stable discharge when we have a reverse anode sheath, as you can see on the plot on top. And there are mainly two cases. which depend on a threshold in the anode magnetic field. So at lower anode magnetic fields, we have a transition, a temporary transition to reverse sheath, and then the sheath goes back to normal operation. While if we increase the anode magnetic field, once it reverses, the discharge cannot be recovered and the thruster shuts off. We can also see that in a reverse sheath condition, the ion current collected at the anode is identically zero, which means that we have only electrons in front of the anode, so the plasma is very non-neutral. Why does the discharge shut off? The discharge shuts off because we can see a complete depletion of the ion density in front of the anode. Here you can see the ion density in the plot on top and its evolution with time. We can see how it's zero basically in front of the anode, and then it's convected away and we don't have any more plasma production and the thruster shuts off. So we couldn't obtain a stable reverse sheath operation, but we obtained a periodic transition to the reverse sheath condition during strong breathing mode. As you can see, and as we thought it would have happened based on the quasi-neutral model, as you can see on the plot on the right, we have the periodic transition to a very negative potential in front of the anode compared to a normal sheath. These transitions are very short. They are roughly 8% of the breathing mode period. And what happens is periodically the ions detach and reattach to the anode. And these results have been submitted for publication to Plasma Sources Science and Technology, and it's currently under review. Well, we need to make the review of the article. For what concerns the methodology on the 2D instabilities, the idea would be to simulate a axial-azimuthal discharge of the whole thruster, but this turns out that it's very difficult to do. So last year I mainly focused on, well, the code in general has been improved with a new approximate Riemann solver and overall efficiency and flexibility of the code that is now extremely flexible and manages to handle two fluid plasma with the 5 moments approximation of two fluid plasma rather well, especially since it has been solved the problem of the Euler-Poisson instability by using a semi-implicit method for updating the potential. And this removes many of the problems that I was facing last year with unstable potential coupling with the ions and electrons fluid equations. So last year I concentrated on the collisional expanding discharge, and I developed a vacuum algorithm to solve some problems of low density, and the results have been presented at the ICBIG conference in the Netherlands. Here is a comparison with the particle in cell code of Enrique Bayo Benitez, and you can see that although there are differences, the overall mechanism of the rotating spoke is very similar. Regarding the whole thruster, fixing the Euler-Poisson instability problem allowed to simulate, properly simulate a whole thruster discharge. This simulation has been carried out for 50 microseconds, which corresponds to roughly 17 million time steps with 500,000 cells. So it's a very heavy simulation, but what we saw is evidence of the turbulent transport, because in this simulation there's no external anomalous transport, and all the transport to the anode is given by some collisions, but mostly this turbulent behavior of the azimuthal electric field and all the other properties. So there are some problems still. The discharge is axially non-stable, and that's because it was a first test and the initial condition were not the most appropriate. Finally, probably more appropriate boundary condition will be used in the future, but it's a very promising result. Currently, I'm doing my research stay at the Laplace Laboratory in Toulouse, and Here I'm working on magnetized plasma column, and the idea is to compare my non-neutral 2D code with a quasi-neutral 2D code called Magnis, developed by Gert-Jan Ageler here at Laplace, on these devices, which may be similar to penning discharges, but they have fundamental differences. And for instance, here we have a virtual ionization, a fake ionization. So basically we inject plasma in this device. We are currently having some problems on the collisional heat flux in the comparison. So for now, we are limiting ourselves on the isothermal case. And this is, of course, an ongoing work. On the right, you can see what we'd expect at 15 Gauss. This is a simulation with my code, and we can see this instability rotating and transporting plasma towards the wall. Finally, here's the scientific production in these years. New are the international, the ICPIC conference of last year, and the future presentation at the International Electric Propulsion Conference this June. And I published, as I said before, an article, and I submitted another one on the one-dimensional model.